Welcome back. This is the beginning of the end, Unit 4, Quantitative Relationships and Chemical Changes. It covers Chapters 7 and 8 in your Inquiry into Chemistry textbook. And we'll start with the unit preparation. So we're going to look at balancing chemical equations. In your textbook, it's pages 254 to 259. And by the end of this lecture, you'll be able to describe the similarities and differences between physical and chemical changes. You'll be able to explain the law of conservation of mass, and you'll be able to balance chemical equations and predict the products of basic chemical reactions. So, the nature of change in matter, there are three levels on which matter can be studied: the macroscopic, the microscopic, and the molecular. And so, the macroscopic, these are things you can see with your own eye. So, and this is how we interact with the world on a daily basis. In the macroscopic world, we can see how things interact without the aid of any technology. The next level would be microscopic, and this would be when we study things like cells. So when you're studying the cells of living organisms, you're looking at the microscopic world, and it requires some technological aid, but it's still not quite at the level that chemistry is working at. Now, chemistry works at the molecular level, and the way I like to word it is, when we look at cells, we need microscopes. Now, if cells had eyes, then they would need microscopes to look at the molecular level. So this is thousands of times smaller than the level of the cell. Especially at the level we're working at. So some of these molecules can only be seen with an electron microscope. So they can only be seen with an electron microscope. And most of the way we describe it is based on how they affect the macroscopic world. So we look at we judge the molecular level, or we describe the molecular level based on its effects on the macroscopic world. So most of what we do is actually based on things that we can't see, or what few people rarely get to see. And so when we're talking about molecular changes, here's some ways we can describe molecular changes. Empirically, these are things that we can generally see with our own eyes. So this would be macroscopic observations. The theory is the molecular description. So this is how we think things are acting on a molecular level. We can't say that it's happening for sure most of the time because we can't actually see it, but based on what's happening on the level that we can see, this is what we think is happening. So for types of changes, one type of change is a physical change, like a state change. And this would be simply something like, melting water. You start with solid H2O, it goes to liquid H2O. So, in terms of empirical descriptions, we don't get any new substances. We still have water at the beginning and water at the end, or maybe it's carbon dioxide, solid carbon dioxide, and gaseous carbon dioxide. In terms of the amount of energy that it takes to do this, it's usually considered to be a small amount of energy. We'll discuss more of this in Chemistry 30, but it's usually measured in kilojoules, and it's in the hundreds of kilojoules. The theoretical description is that there are no new molecules. So we started with water molecules to begin with. We end up with water molecules in the end. The things that are changing are the intermolecular forces. So in solid water, our water molecules are held together by hydrogen bonding. They form a nice crystal lattice. As that water heats up, the water molecules start to move a little bit faster until they start breaking some of those hydrogen bonds. And as they break those hydrogen bonds, they flow around each other in a liquid state. So it's only intermolecular forces that are broken for a physical change. When we move up a level, when we get to a chemical change, and these are mostly what we're going to be talking about, so these for us are the important ones. we can tell that something's happening because we usually end up getting something new. So a new color or a new odor or a new state. This means that, and we usually see new substances. Sometimes we're getting solids and liquids and gases, but they're often of completely different chemicals than what we started with. Those new chemicals have new permanent properties. In terms of energy change, it's a medium energy change. It's still measured in kilojoules, but it's usually in the thousands of kilojoules. So it takes a bit more energy, or involves a bit more energy change than a physical change. In terms of the theory, we're saying that old molecules are breaking and forming new molecules. So what's happening is the atoms are changing their arrangement. Some of the atoms that used to be together are separating from each other and joining with other atoms. The chemical bond's broken and they're remade. So these are usually either ionic or covalent bonds that are broken. These are the bonds we're talking about when we talk about chemical changes. One level above that are nuclear reactions. These often emit radiation, so small subatomic particles are often given off by these reactions. And you've heard probably the terms alpha particles and beta particles. We're going to ignore them for now because they aren't part of what we need to discuss. Often this requires new elements to be formed. So this is the whole starting with, say, hydrogens and getting heliums. So we're actually rearranging the number of protons that are inside an atom. This takes enormous amounts of energy change. It's measured in gigajoules, or thousands of gigajoules. Huge amounts of energy change, or more. So thousands of gigajoules, so often 1,000,000 times more energy is involved in a nuclear reaction than there is in a chemical reaction. And the theory is we're getting new atoms and the nuclear bonds are broken and made. And we don't talk about these very much, but what we're really doing is changing the number of protons inside an atom. So those are the three types of changes we are going to be talking about, for the most part, chemical changes. So, now how do things react, or how do chemical changes happen? And the way we're going to describe it is we're going to describe it using kinetic molecular theory. And the idea is we start with a couple of atoms. And these atoms, here we have a hydroxide ion. It's an oxygen bonded to a hydrogen, and the whole thing has a negative charge on it. And it's bumping into bromomethane. So we have a carbon, and then 3 hydrogens, the little red balls there, and we have a bromine molecule, or a bromine atom. If these things hit the right way, then a chemical reaction can occur. And in order for a chemical reaction to occur, they do have to hit in the right configuration. So in this case, a chemical reaction only occurs if our oxygen bumps into our carbon. If these two molecules bump, they can form a bond. When they form a bond, when they start sharing electrons, a bond is broken on the other side. And so what you end up getting is something like methanol. So you end up with the OH group bonded to our methane. The bromine got knocked off, and it's now a free molecule. And that's a chemical reaction. In terms of writing this in something that's a little bit more familiar, or will be familiar, is we'd write something like this. We have a hydroxide. It reacts with CH3, Br. The transition state we represent with an arrow. So something has to happen. They have to hit the right way. If they do, we end up getting CH3OH. So we get our methanol molecule plus a bromine ion. And so that's the basic structure of a chemical reaction. So kinetic molecular theory says the smallest particles of a substance are in continuous motion. They're always moving around. We knew that when we talked about gases. The particles we're talking about can be molecules or atoms or ions. And when particles collide, that's what causes a change in matter. When two particles collide, something has to happen. Bonds have to be broken and bonds have to be reformed. these bonds are represented by either the sharing of electrons or the transfer of electrons. So these particles move in erratic patterns, and when they collide in a certain orientation and with the right amount of energy, if these molecules are moving too slow, then even if they hit, nothing might happen. So they have to be moving at with a certain amount of energy, hitting a certain way, and if they do, then a chemical reaction takes place, and this is the collision reaction theory. So it says that collisions are what cause reactions. Now, during a chemical reaction, a couple things that we have to remember. The total mass before the reaction will always be equal to the total mass after a reaction. And this should make sense. Since the chemical change is thought to be just a rearrangement of molecules, then the mass must remain constant. We're not losing any of these atoms. These atoms aren't disappearing or reappearing or coming from nothing or whatever. So even though we're rearranging the molecules, since they're all still there, the total mass before and after must remain constant, and that's just what this says in bold. So each atom from the reactants must exist in the products, and this is the basis on which we're going to write our chemical reactions. So balanced chemical equations represent chemical reactions. We know that the total number of each kind of atom or ion in the reactants is equal to the total number of the same kind of atom or ion in the products. And so here's an example. When you have carbonic acid, it decomposes to form water and carbon dioxide gas. Now, if we take a look, we can see that in our original, so here we have our reactant. Here we have some kind of transition state, which we're not going to worry about. So something has to happen to this molecule to make it break down, and then we end up with products. So it's really a before and after picture. Before anything happens, we have carbonic acid. After something happens, we have water and carbon dioxide. When we take a look at the equation, we can see that we have 2 hydrogens on the reactant side, and we end up with 2 hydrogens on the product side. We have 1 carbon atom on the reactant side and 1 carbon atom on the product side. When we look at our oxygens, there are 3 oxygens on the reactant side, and so we have to have 3 oxygens on the product side as well. So every atom that we have as a reactant has to be accounted for as a product. And so the same holds true with the next reaction. Sulfurous acid can also decompose. If you take a look, the number of hydrogens on either side of the arrow is the same, the number of sulfurs on either side of the arrow is the same, and the number of oxygens on either side of the arrow is the same. Another reaction, we know something happens with this one. Every time ammonium hydroxide goes into water, it decomposes into ammonia and water. And if we take a look, we still have a balanced chemical equation. We have 1 nitrogen, 4 plus 1 would be 5 hydrogens. So we need a total of 5 hydrogens on the other side. There's 3. There's 2 more. So as long as the totals are the same, we know we're doing okay. And there's 1 oxygen on either side as well. So here's what chemical reactions mean. A formula shows chemistry at a standstill. It tells you what a substance is. Equations show chemistry in action. They have 3 parts. The reactants, which enter the reaction, and the products are formed by the reaction. We also need to usually know the amount of each substance used and the amount of each substance produced. 2 important principles. When we write down the formula for a compound, that can't be changed. If we are saying that water is formed, then we have to have water as a product. It has to be H2O. It can't be anything else. So when we're balancing our chemical equations, we always choose our products first, and those products have to keep the chemical formula we give them. You can't balance an equation by changing a chemical formula. Not allowed. We got to make sure that every atom that is produced has to be accounted for from our reactants. So this is the basis, or this is how we apply the law of conservation of matter, which states that in a chemical reaction, atoms can't be created or destroyed. So when we're balancing our chemical equations, there's a couple things we need to keep in mind. All of these elements listed here, hydrogen, nitrogen, oxygen, fluorine, and so on, they are diatomic molecules, which means if they occur as an element in the reaction, then they are diatomic. They occur as an O2 or an N2 or an H2, never as just oxygen as an O or hydrogen as just an H. They always exist in the diatomic form. The arrow sign means yields. It shows the direction of the action. It lets you know which side is the reactants and which side is the products. If you do see a double arrow, and now in my slides, we've already seen some with acids and bases, I use that two-headed arrow most of the time. What you'll see, however, is something that looks like this. And it means that not all of your reactants actually reacted. Some of them didn't. And that the reaction is at equilibrium. And before we get into balancing our equation, we're going to make sure all of our formulas are right. We never want to change a chemical formula during the balancing of an equation. And the balancing is done by placing coefficients in front of the formulas to ensure that the same number of atoms on each element are on both sides of the arrow. And then after that, we worry about states. If the reactant's a solid, we put a little S beside it. If the reactant or product is a gas, we put a G beside it. And if it's a reactant or product that's in water and it dissolves in water, and it's soluble, so if it's soluble, then we write an aqueous after it. And unless otherwise said, all of our reactions are going to occur at SATP. So, the first thing we need to do when we balance our chemical reactions is we write down the chemical formula of each reactant and product, including the state for each. And then the easiest way to go through it, it doesn't always work, but 99% of the time it does. You balance the atom or ion that's present in greatest quantity. And then you balance the atom or ion that's in the next greatest quantity, and so on. Then double check and make sure that everything's balanced. So you're going to check to make sure that the numbers you put in there actually balance the reaction. Alright, so the easiest way to learn how to do this is by example. So we'll start with a reaction. Magnesium oxidizes when exposed to air. We're going to write the balanced chemical reaction. So the first thing we've got to do is write down our reactants, remembering to check for diatomic or polyatomic atoms or species, and we're going to write the states. So when we have magnesium and it's oxidizing, we write magnesium solid, just as we see it on the periodic table, and O2 gas. Notice that it's oxygen, and oxygen is one of those diatomic molecules, so we have to write it as O2. The next thing we do is we're going to predict the products using our ion formation theory. So we know that magnesium, when it reacts with a nonmetal, it forms magnesium 2+. And I know I have this already on the slide, so what I'm going to do is just erase this stuff here. And so, magnesium can form a 2+ ion, oxygen forms a 2- ion, and this is how we determine our product. If this thing is going to form a product, then it has to form a product based on the ions that are formed by the two atoms. And so the product that we're going to get is MgO. The 2+ on the magnesium and the 2- on the oxygen, so we get a compound with a charge of 0. Got to make sure we get the state. All ionic compounds at SATP. This is an ionic compound. And this is just a little reminder from Unit 1. All ionic compounds are solid at SATP. And then we balance it using coefficients. So we never change the formulas during this balancing. And here's the way we do it. We take a look and we say, well, the most common atom in this reaction is oxygen. There's a total of 3 oxygens kicking around. And so we'll balance that first. And we have 2 oxygens on one side. We only have 1 on the other side, so we're going to balance it by putting a 2 in front of our magnesium oxide. We can't put it down here because that would change the formula. And then that one's balanced. And then we say, well, now that our oxygens are balanced, let's make sure our magnesiums get balanced. And we take a look and we say, well, there's 2 magnesiums on the product side. There's only 1 on the reactant side, so we put a 2 in front of our magnesium on the reactant side. And then we check. 2 magnesiums on the reactant side, 2 magnesiums on the product side. 2 oxygens on the reactant side. This 2 in front of our compound gets carried to every atom in the compound. So there's 2 magnesiums and there's also 2 oxygens. So everything's balanced and that would be our balanced chemical reaction. Let's try another one. So here we have zinc metal being placed in hydrochloric acid. Predict the products. The first thing we do is we write the reactants. Remember to check for states. Since it said hydrochloric acid solution, we know that our hydrochloric acid is going to be aqueous. Zinc is a solid metal. And then we check out what ions you could possibly have. So zinc forms a 2+ ion, hydrogen forms a 1+ ion, and chlorine forms a negative ion. Now, the zinc and the hydrogen, they can't get together. They're both positively charged, so they'd actually repel each other. The hydrogen and the chlorine could get together, but then we'd end up with what we started with. So there's not much of a reaction happening there. The only other thing that could happen, really, is this zinc and this chlorine can get together. If they do, then we have to make our compound based on their charges. So zinc is 2+, chlorine is 1-, and so the product we get is zinc chloride, where we have 2 chlorines for each zinc. The other product we get would be hydrogen. And because hydrogen, this is a diatomic molecule, hydrogen never exists as just H. That thing never exists. So we write it as H2. We get our states. Zinc chloride is aqueous when we check our solubility table, and hydrogen gas is a gas, so it's going to form gas and bubble out of that solution. Next, we have to balance it, and so we balance it using coefficients in front of each element or compound. And again, we start with the most common thing. So here we have a choice. We can choose. There's a total of 3 hydrogens kicking around on either side of the equation, and 3 chlorines. We can start with either one. I'm going to start with the chlorines just because. So if I take a look, I have 1 chlorine on the reactant side. I have 2 chlorines on the product side. So I'm going to put a 2 in front of my HCl to balance out my chlorines. Now I have 2 chlorines on either side of the reaction. Now that those are balanced, I'm going to check out my hydrogens. So I now have 2 hydrogens on the reactant side and 2 hydrogens on the product side. So my hydrogens are balanced. The next thing I check is my zincs. I have 1 zinc as a product, 1 zinc as a reactant. My zincs are balanced. So there's my balanced chemical equation. Note that I didn't change any formulas. And there we have it. Now, for most of your chemical reactions, you don't have to write the reaction out 8 or 9 times and do one little step. So here's how it would normally look. Oops. So a white precipitate forms when a solution of barium chloride is mixed with a solution of sodium sulfate. And so the first thing we need are some reactants. So barium chloride would be BaCl2 because barium forms a 2+ ion, chlorine forms a 1- ion, plus sodium sulfate. We're going to get Na2SO4. Again, sodium forms a 1- ion, sulfate forms a sodium forms a 1+ ion, sulfate is a 2- ion, so that would be the balanced chemical formula for that. And then we check out our states. We were told that we have a solution of barium chloride, so we put a little AQ there, and a solution of sodium sulfate, a little AQ there, and we draw a reaction arrow. And in order to predict the products, we're going to just take a look at our reactants, and we're going to say, well, the ions formed are Ba2+, Cl-, Na+, and SO4, 2-. So those are all the ions. Now the barium's already with the chlorine, so them getting back together would be kind of boring. So what's going to happen is really we're just going to switch our positive ions around. So the barium is going to end up going with the sulfate ion, and the sodium and the chlorine are going to get together as well. And so the way we determine our chemical formulas is based on the charges on our ions. And it doesn't matter which one we write first. I'll write the sodium chloride first. Sodium chloride is NaCl. When we check the solubility table, we find out that it's aqueous. And our other compound is BaSO4. When we check the solubility table, we find out that it is not aqueous. It's not soluble, so we write an S beside it, and that would be our white precipitate. This white precipitate is our barium sulfate. And notice that when I got these two chemical formulas, I didn't check to balance my equation when I made them. I made them independent of my balancing because that's the way we do it. The type of compound formed has nothing to do with how the equation gets balanced. And now that we have our compounds, we can balance our equation. And so we take a look, and the most common ion is either going to be our sodiums or our chlorines. We can start with either. I'll start with sodiums. We have 2 sodiums, so I put a 2 in front of my sodium chloride. When I take a look at my chlorines, I have 2 chlorines here. I now have 2 chlorines on my product side. I have 1 barium on my reactant side, 1 barium on my product side. So those are balanced. 1 sulfate ion and 1 sulfate ion. Since the whole sulfate ion moved as a unit, it started with sodium, it ended up with barium, we're going to balance it as a unit as well. So the SO4, since none of it broke apart, when we balance it, it's easier to balance it as a sulfate than as a sulfur and 4 oxygens. It's just less counting. And so I'm just going to write it out nice and neat here. So our final reaction would be BaCl2 solid plus Na2 SO4 aqueous two sodium chlorides and a barium sulfate. Now, when you're writing down your chemical formulas, make sure that capital letters look like capital letters and lowercase letters look like lowercase letters. And also make sure your subscripts are subscripts. So this is very different from this. This is a carbonate ion, probably 2 negative. This here means 3 cobalt or atoms. So they mean very different things. So you got to be really clear with your capital letters and lowercase letters. If it's a capital O, make sure you draw it as a capital O. Otherwise, we'll end up getting some strange compounds. So, when we're balancing some reactions, here are some tips. Tip number 1, stay calm. Sometimes chemical equations are more complicated to balance than other ones, so it's important to stay calm and follow the steps. If it didn't work the first time, erase everything and start over again. The first thing you're going to do, if you're having problems balancing an equation, double check your chemical formulas. Often this is the mistake that's made. Instead of a carbon dioxide, you write carbon monoxide, and it messes the whole thing up. So, if polyatomic ions remain together through a reaction, balance them as a single unit. We did that with the sulfate ion. It just makes life easier. The other thing we're going to do is delay balancing atoms present in more than one compound until all the other stuff is balanced first. So, for example, especially when we're working with combustion reactions, we're going to end up with often, in a combustion reaction, we often end up with water and carbon dioxide. Because there's oxygens in both compounds, we're going to balance the oxygen last. It just makes it easier to do. Always balance elements in their pure form last, and then, so the same thing with this combustion reaction. Most of the time, we're reacting gaseous O2. Sorry, I'll write it up here. So, when we have things like O2 all by itself, or H2 all by itself, we're usually going to balance those things last because it's just easier. Once everything else is balanced, we can throw whatever number we want in front of those single elements, and it only changes that one element. So it just makes things easier if we balance them last. If we end up with fractional coefficients, then what we're going to do is multiply the equation by the denominator of that coefficient. And I'll do an example just because it makes it easier. So, when exposed to a flame, ethanol combusts to form carbon dioxide and water according to the following unbalanced reactions. So here, we were given all of our compounds. And now we're going to balance our equation. So the first thing we want to do is balance the atoms or ions present in greatest quantity. And so when we take a look, probably one of the easiest things, or the thing in greatest quantity, would be hydrogens. Here we have 6 hydrogens total, so we need 6 hydrogens total. So we put a 3 in front of our water, and now we have 3 times 2, so that's 6 hydrogens there. The next thing we're going to do, now because oxygen is by itself in this compound, or element, and because it exists in all of our compounds, we're going to balance that one last. If we start trying to balance it first, we're not going to know which compound we want to change. In order to balance it, right now we have 3 oxygens as reactants. And look at that, we have 3 oxygens as products. So right now, actually we don't, sorry. We have 2 oxygens here and 5 oxygens here, or another 3, so a total of 5 oxygens on our product side. And the biggest problem is we don't know which compound we should change in order to balance it. If we put a number here, then all of a sudden it changes the number of oxygens and the number of carbons. And so we end up changing things we don't want to change. So the next thing we're going to balance is our carbons. And if we take a look, there's 2 carbons on our reactant side, only 1 on our product side, so we'll put a 2 in front of our carbon dioxide. So now our hydrogens are balanced, our carbons are balanced, and now we can worry about the oxygens. On the product side, we have 4 plus another 3, so we have 7 O's on the product side. On the reactant side, we have 3, or 1 plus 2. And so to balance it, I could start putting coefficients in front of my methanol here, or ethanol. If I do that, though, it changes the number of carbons, the number of hydrogens, and the number of oxygens. So all of a sudden, I got to go and rebalance my products. So that's not the place we want to put it. Instead, we're going to balance this off by putting things in front of our oxygen. So we have 1 over here. In order to get 7 total, I'm going to put a 3 here. And now I have 1 plus 6, so there's my 7 oxygens. So there's my balanced chemical equation. And here it follows through the same steps. So we balance our hydrogens first, then we balance our carbons, and finally we balance our oxygens. Now how did I end up with 7 over 2? And that there is a typo, so 6. And so if it was 7, then we double everything, and we're just going to ignore this one for now because it's a typo. So now we're going to go through and just balance some equations. What I would suggest is hit and pause on the old recording and go through this list of equations and just balance them on your own, and then hit play and see if you get them right. So we'll start with this first reaction. And to balance this off, because we have more hydrogens than anything else, that's where I would start. I have 2 on the other side, those are fine. Then I go to my oxygens. I have 2 oxygens, I only have 1 oxygen, so I'm going to put a 2 there. Notice that because I changed the number of water, or the number of waters, I've also changed the number of hydrogens. So I now have 4 hydrogens on my reactant side, or product side. I'm going to need a total of 4 on my reactant side. For the next one, same sort of idea. Start with the thing that's most common. So we're going to start with our hydrogens. On this side, I have 8 hydrogens, 4 times 2. So on this side, I need 8 hydrogens. So I'm going to put a 4 in front of my H2O. Now my hydrogens are balanced. The next thing I'm going to look at, I'm going to leave those oxygens till last because they're everywhere. The next thing I'm going to look at is my nitrogens. I have 2 nitrogens on my reactant side. So I need 2 nitrogens on my product side. Next is sulfurs. 1 sulfur here. So I need only 1 sulfur as a reactant or a product. Now you don't have to when you're doing it on your own, but when you're doing the fill in the blank questions, if there's a 1 in front of a compound, you got to put it in the fill in the blank. So we'll put a 1 there just to make sure that we know it's done. And now we're going to balance our oxygens. So on this side, I have 4 oxygens plus another 2 plus another 4. And so that gives me 10 oxygens. So I'm going to need a 5 in front of my O2 to get 10 oxygens. The next one, again, take a look at something that's common. Here I have 2 silvers and 3 silvers total. The nitrates, I have 3 nitrates total as well. So I'm going to balance either of those first. It doesn't matter. I'll start with my silvers. I have 2 in my product side, so I need 2 in the reactant side. That balances my nitrates nicely, and notice that I'm balancing them as a unit. So since the NO3 stuck together, it was NO3 before the reaction started, and NO3 when the reaction was done. I balance them as a group. So I have 2 NO3s on my reactant side and 2 NO3s on my product side. Next I go to my zincs. I have 1 zinc, that's all good, and 1 phosphate and 1 phosphate, so that's all good. So just so that we know, I'm going to put 1s in front of all these compounds again. When you're writing them on your own, you don't have to, but when you're doing a fill in the blank, you do. Now we'll balance another one here. Here we have bromine reacting with aluminum chloride, and we can balance either, I would say either the chloride or the bromides first. So to balance my chlorines, I have 3 chlorines on this side and 2 on my product side. Now I have to balance them using coefficients, and since 2 and 3, I can't put a 1 or a 2 in front of this chlorine and make them equal, but what I can do is go like this. And now I have a total of 5 chlorines on my product side and 5 chlorines on my reactant side. And then I go through and I balance my bromines, and we can do the same trick. There's 3 bromines on my product side, there's 2 bromines on my reactant side, so we can balance those by going 3 and 2. And we'll just check to make sure our aluminums are balanced. Here I have 2 aluminums on my product side, or reactant side, and another 2 aluminums on my product side. One more equation here. So nickel sulfide reacting with oxygen, and then we get nickel oxide and sulfur. So now we're going to balance this one out. And because oxygen's all by itself on my reactant side, I'm going to leave that one till last. So my nickels look good, and my sulfurs look good. So now we're going on to our oxygens. So right now we have a 1 there, and we have a 1 there, and a 1 there. Now if we take a look, oxygens, I have 3 oxygens on this side, on my reactant side, and only 2 on my reactant side, sorry, product side, reactant side. So to balance this, what I'm going to do is I'm going to call this 3 over 2. And when I do this, 3 over 2 times the 2 will give me the 3 oxygens that I'm looking for. Now, because we always want whole number coefficients, and we don't have a whole number here, we're going to multiply the whole equation by 2. And when we do that, it clears our denominator on our fraction, but it causes everything else to double. So we're going to end up with a 2 here. The 3 halves becomes just a 3. The 1 becomes a 2, and the 1 becomes a 2. And so our balanced chemical equation, I'm just going to erase all that stuff and write it out nicely once. After we double everything, we're going to end up with a 2, a 3, and a 2, and a 2. There we go. All right, pointer options. And so we end up with a 2, a 3, a 2, and a 2. And for now, we have to make this a whole number. So at the moment, no fractional coefficients. Okay, so there's the homework on page 258, questions 1 and 2, and we'll see you in the next lesson.